Today we're going to shift gears dramatically from our first unit, start a new unit called Electric Forces and Fields. We're going to talk for the next several weeks about electricity. And we're going to start off this discussion about electricity by looking at the most fundamental aspect of it, and that is the two types of charge. I didn't cover this up and uncover it like I usually do with stuff because I think, gentlemen, that this, what you see up on the board right now, is common sense. We know this, right? My son's in grade 6. I'm pretty sure that he knows there's positive charge and there's negative charge. What he might not know is where positive charge comes from and where negative charge comes from. Well, it all comes down to the atom. There's your hint. It all comes down to the atom. Knowing that, can anybody tell me where positive charge might come from as a result of an atom or atoms? Sorry? The nucleus. So what's in the nucleus? There's three constituents of the atom, right? There's the protons. What else is in the atom? Neutrons and good. And what's part of the nucleus? The protons and neutrons. Well, one of those things in the nucleus is neutral. What do you think it would be in the nucleus that's neutral? A proton or a neutron? Neutron would be neutral, therefore the proton would be positive. So the positive charge comes from having protons in the nucleus? Yes, ultimately it is. Okay, positive charge ultimately comes from having protons. But sometimes we have a positively charged object. Let's say you rub a balloon against your hair and the balloon becomes positively charged, your hair becomes negatively charged. Does that mean that the balloon consists only of protons? No, not at all. There's lots of neutrons in your hair and in the balloon. There's lots of electrons in your hair and in the balloon. So how does the balloon become positively charged if it has both protons and electrons as well as neutrons? Go ahead, Emma. Good. So positive charge results from having more protons than electrons. See the symbol there for protons, guys? P plus, E minus, just a little bit of shorthand so we don't have to write out the words protons and electrons. Is it ever possible to have just protons? Well, in very, very limited cases, yeah, it would be. If you have a hydrogen ion, or a hydrogen, or a nucleus, an alpha particle, which you're going to learn about in our last unit, yeah, it's possible to have no electrons present there. When we're talking about nuclear decay, radioactive decay, sometimes we don't talk about the electrons. But in normal circumstances, we've got both protons and electrons. It's positively charged if you have more protons than electrons. Electrons are the negatively charged things, by the way, right? So that means a negatively charged object comes from having what? Not just electrons, right? But rather more electrons than protons. Now, what about a neutral object? Yeah, I'm not even going to write that one down. They've got the same number of protons as electrons. Now, I got a question for you. We can move charges around, right? We talked about that just a little bit already. You rub a balloon against your hair, you put the balloon against the wall, and it sticks to the wall. Okay, the balloon didn't stick to the wall before you rubbed it against your hair. Charge must have been transferred either from the balloon to your hair or from your hair to the balloon, one of the two. What kind of charge is going to move? If something's going to move, protons or electrons, what is it that's going to move? Why electrons? You're right, by the way, it is electrons. Good answer. Protons are held really, really tightly in the nucleus. Now, that might not make a lot of sense to you on first glance, right? We think, well, protons, they're all positive, and one of the laws of electric charge that we're going to refer to in just a few minutes here, or review in just a few minutes, but that you've heard before, one of the laws of electric charge is, like charges repel each other, right? Positive repels positive. So the protons should push the protons apart, and the nucleus should explode. But there's also a force within the nucleus called the strong nuclear force that over very, very small distances is really, really big. It keeps the nucleus together, and it keeps it together tightly. So those protons that are in the nucleus, they don't want to leave. It is conceivable, it is possible for them to leave, but then it's not an electrical interaction, then it's a nuclear reaction. Okay, that doesn't normally happen, the nuclear reaction. So it's not going to be the protons that are going to move around when I rub the balloon against my hair. It's going to be the electrons because they're less tightly bound. They're outside the nucleus, orbiting around, and they're held together. They're held into the nucleus by an electric force, but it's a much weaker force than that strong nuclear force. So it's a lot easier to energize them to the point where they can leave than it is to do the same thing for the protons in the nucleus. So if something's going to move, it's going to be the electrons. Here's the unit of charge. Okay? Kilometers per hour could be a unit for speed. Meters per second is the standard unit for speed. Joules is the unit for energy. Newton seconds or kilograms meters per second is the unit for momentum or impulse. Well, the unit for charge is a coulomb. Now, coulomb measures a very, very big amount of charge. A coulomb is a big unit of charge. Just like, say, a light year. A light year is a unit for distance. That's a really, really big unit for distance. A millimeter is a small unit for distance. A light year is a big unit for distance. The distance that light travels in 1 year. So we have different units to describe varying amounts of quantities. A coulomb is a really big unit, just like a light year is a really big unit. In fact, it would take approximately this many electrons, okay, to this order of magnitude of electrons, in order to get a single coulomb. That's a lot of electrons. It would take about that many electrons, and you don't have to write down that number. It would take about that many electrons to get a single coulomb of charge. Okay, a coulomb is a lot of charge. It could take that many electrons to get that much charge. Now, it's such a big unit of charge that we often see a coulomb, we often see a unit of charge written as a microcoulomb, which is 10 to the minus 6 coulombs. Or sometimes we see it even written as a nanocoulomb, which is 10 to the minus 9 coulombs. When we're doing a calculation, we always have to go back to the coulomb. But we often see it in a question as a microcoulomb or a nanocoulomb, or conceivably even something different, because those are more usually a measured charge. It's just like a light year can measure distance. It's not convenient to measure the distance from this side of the room to that side of the room. Just like a light year can measure distance, a coulomb can measure charge. But sometimes it's not convenient to use a coulomb to measure the energy. Sometimes it's more convenient to use a coulomb. But when you're doing calculation, you always have to go back to that. It's an easy conversion, as long as you know the prefixes. All right, so it takes about that many electrons to make up a coulomb of charge. What exactly is the charge of an electron? Well, minus 1.60 times 10 to the minus 10. So it takes about 10 to the 19 electrons to make up a coulomb. Anybody want to take a stab at what the charge of a proton might be? Oh, come on, you can get this. How would you have ever remembered, how would you have ever known that the charge of an electron is negative 1.6 times 10 to the minus 19? We probably haven't even learned that in chemistry. I don't know, have you learned that in chemistry at all? No? 10 to the negative 19. Bailey, what do you think the charge of a proton might be? Yeah. Right? We didn't know until 1 minute ago that the charge of an electron was negative 1.6, nor the charge of the proton was positive 1.6, but we knew they were the same. So if we now have the charge of the electron, well, we'll also now have the charge of the proton. Positive 1.6 times 10 to the positive 1. What would the charge of a neutron be? Daniel? No, it's 10 to the negative 19 still. It's just type of charge you have. Positive. The exponent's still the same amount of charge, just opposite. What's the charge of a neutron? How many coulombs? 0. Neutron, right? All right. Take a look at your data sheets here. take out your data sheets. I want you to flip to the page that's titled Physics Data Sheet. And I want you to find for me on that data sheet the charge of the electron. And the charge of a proton for that matter. Who's found it? Who's found the charge of the electron? Tom, where is it? Top right on a particle that says charge of an electron. Okay, there we go. Minus 1e, the charge of proton, plus 1e, alpha particle, neutron, fermions, positron, electron, neutrino. We don't even know what some of that stuff is right now, right? You will, by the way, by the end of the year. Okay, we're not going to worry about some of that stuff right now. We're going to focus on the proton and the electron right now. Minus 1e, plus 1e. Didn't I say that it was minus 1.6 times 10 to the minus 19? Positive? 1.6 times 10 to the minus 19? Oh, what's an E? An E is what we call the elementary charge. Smallest charge you can have. Take a look over on the left-hand side for the value of the elementary charge. 1.6 times 10 to the minus 19 coulombs. So an electron would be minus 1 times 1.6 times 10 to the minus 19 coulombs, and a proton would be plus 1 times that. It's not hard to find, okay, as long as we know how to find it, as long as you know where to look. Okay. On your next unit test, which would be a few weeks down the road, maybe even your next quiz, which will be a couple days down the road, you may need to use the charge of an electron. I won't give it to you. Okay, you can find it on your data sheet, but just again, be familiar with how they express it on your data sheet. Minus 1e, which is minus 1 times this, or plus 1e, which is plus 1 times that. Honestly, okay, within the next week, you'll probably just remember the charge of the electron and proton, because you'll use it enough times. But know where to find it and know how to find it if you don't remember it. Okay, 2 more terms. Conductors and insulators. You guys have all heard this before too, in the context of electricity, but also in the context of heat. We're obviously referring to conductors and insulators in the context of electricity, not heat. What's an electrical conductor? Metal, okay. So a metal would be typically a good example of an electrical conductor, but it's not a definition. Now, there's a lot of different types of metals, right? And all of them have varying conductivity. Some are better than others. Silver is a really good conductor. Copper is a really good conductor, but some metals aren't as good as others. But generally, metals tend to be the best conductors. You'll see why in just a couple minutes here. Kenton? Okay, anything that kind of allows the flow of electrons. Now, why would something allow the flow of electrons? Why would something allow electrons to move, flow from one place to another? Because the protons? No, not so much. Because the electrons in the outermost regions aren't as tightly bound there. Now, those of you who've taken chemistry, what types of materials generally have electrons in the outermost regions that are freer to move? Metals, right? That's why metals are good conductors, generally, because they have those electrons in the outermost regions that are free to move around. Versus an insulator, which, of course, is going to be just the opposite, right? The electrons are more tightly bound to the nucleus and not as free to move around. Bailey gave me the general good example of a conductor, metals. Somebody gave me an example of a good insulator, or in other words, a poor conductor. Yeah, styrofoam, good. Okay. What's another one? Plastic, generally, yeah. Rubber, wood. This is just a spectrum. It's a spectrum, like spectrum. This is kind of like a spectrum of conductivity. It shows different materials with varying degrees of conductivity. relative magnitudes of conductivity. So it's not giving us any kind of unit for the amount of conductivity. It's just saying relative, one thing relative to another is this much better or this much worse of a conductor. You can see that down here in these, what we call semiconductors, which are some properties of conductors, some properties of insulators. If we say that's 10 to the 0 in there, which is 1, right, 1, okay, then silver is a great conductor. It's 10 to the 8 times better, 100 million times better of a conductor than something that has a conductivity of 10 to the 0 or a conductivity of just 1. Right? It's 100 million times better. Copper is a good conductor as well. Aluminum is a good conductor. We used to use aluminum wiring in houses. Now we use copper wiring in houses. They're both really good conductors. The switch was made from aluminum to copper wiring in houses, not because copper is a way better conductor, although it is slightly better than aluminum. The switch was made in houses because aluminum likes to arc. You know what that means? Electrons like to jump from one piece of aluminum to another really, really easily. What's the problem when that happens inside your wall? Fire, right? Your house burns down. So they're not allowed to use aluminum wiring in houses now because it's just not safe. So we use copper wiring. It's still possible for copper to arc as well, but it's a lot less likely to arc. And it's a good conductor. The problem with copper is, especially now, it's very, very expensive. Okay? The last 5 or 10 years, copper has become, the price of copper has skyrocketed. So much so that people actually like steal copper. Like people actually will go into, electrical facilities and cut off the power, and then cut out some of the copper wiring and steal it, and then sell it. Copper's so valuable now. Not quite like gold. Silver. Hey, what about silver? Silver's a really good conductor. Why don't we use silver in our houses? Well, it's expensive, right? Gold's a very good conductor too, by the way. Very, very good conductor. Obviously, we're not going to use gold as wiring in our houses. That would be ridiculous. But we do use gold in some places for conducting electricity. Where have you seen gold used? Where have you, each one of you, probably seen gold used as a good conductor? A lot of times when you buy a cable, what does it say about the end of it? Gold plated, right? It's a very, very thin layer of gold, so it's not very much gold at all, okay, but it's still gold, right? And it's used because it's a very, very good conductor. And cables, whether, no matter what it's transferring, whether it's sound, right, or whether it's information or whatever, it's really transferring an electrical signal and converting it to the sound or to the information. You can take a look at some of these things that are bad conductors or good insulators. Wood, glass, rubber. Rubber is about 10 to the 14 times worse than a semiconductor conducting, which is about 10 to the 22 times worse than silver as a conductor. You don't need to remember these numbers. You don't even need to remember the order of this. You don't even need to remember all the examples of this. But in general, I want you to remember that, okay, look, the good conductors are usually metals, although there are varying degrees even within that. And the bad conductors, things like wood, glass, rubber. Okay, the bad conductors or the good insulators. Right, Kenton? Okay, a couple more things here, guys, and then we'll take out our static bulb and see what we can do with Kenton's hair today, okay? 3 laws of electric charge. These aren't new to us. Okay, they might be new in the way that they're being formulated to you here right now, but nothing is going to be surprising to you here when you read this. Opposite charges attract each other. What does that mean? Well, positive attracts negative. Okay, we know at some level we know that. Positive attracts negative. Like charges repel each other. It means positive repels positive. Or if you don't know what that word repels means, pushes away. Positive pushes positive. Positive pushes, or pulls, I should say, negative. Opposite charges attract. Okay. Negative pushes negative. Like charges repel. And the third one, finally, charged objects attract neutral objects. There's a couple words in there that are really important. Charged objects, neutral objects. Okay. Positive doesn't attract doesn't attract neutral. Negative doesn't attract neutral. A proton does not attract, electrically at least, a neutron. An electron does not electrically attract a neutron. But yet, a negatively charged balloon that you've just rubbed against your hair will attract the neutral wall. Charged objects attract neutral objects because there are in that neutral object both positives and negatives. So it's not enough to say that positive will attract neutral. It won't in every case. But a positive object will attract in every case a neutral object that has both protons and neutrons in it. We'll talk tomorrow or the next day, depending upon a decision that I'll make later today. We'll talk a little bit more about why that's the case, why it has to be an object as opposed to something as simple as a proton and a neutron. The bottom line is, it's got to be an object. For today, you're just going to have to trust me on that, okay? Tomorrow or the next day, I'll tell you why. Charged objects attract neutral objects. Okay, one final law, and then I want to take a look at a couple example questions, and then we'll pack it up for the day. I'm going to cover this one up. See if you can figure this one out. You should be able to. The law of conservation of energy says energy can't be created or destroyed. It can be transformed or transferred. But the law of conservation of mass says that mass can't be created or destroyed. That's a chemistry thing, right? The law of conservation of momentum says total momentum remains the same. In other words, momentum can't be created or destroyed. So the law of conservation of charge would say what? Charge cannot be created or destroyed. Good. Now, we can move it around. We keep talking about that balloon being rubbed against the hair because we've all done that, right? You rub the balloon against your hair, charge gets moved around from either the hair to the balloon or the balloon to the hair. But the total amount of charge that you start it with before you rub the balloon against your hair is the same as you end with after you rub the balloon against your hair. I asked this question a little bit earlier. I'll ask it again. When charge is transferred, what type of charge is it that's transferred? What is it that's moving from one place to the other? Is it the protons? Is it the electrons? Electrons. Because they're not as Kenton said before, they're not as tightly bound to the nucleus as the protons are. Protons are stuck where they are, unless you have a big nuclear reaction, which is a whole other ballgame entirely. Then the protons they're stuck there. They're going to stay there forever. If you move the protons, what happens? What do you do to the atom if you move the protons? If you take a proton out of this atom and move it over to this atom, then what have you done? You made a new atom, right? You've changed the atom itself. It's alchemy, right? And we don't normally do that. Okay, not chemically, at least, just by some kind of nuclear reaction. So what kind of implications does this have? Well, let's take a look at one. There's a lot of implications, some qualitative, some quantitative. Here's one quantitative implication. We'll talk about some more as the days go on here. We've got three objects here. We're calling them ball number 1, ball number 2, and ball number 3. Ball number 1 starts with a charge of 3 coulombs. Ball number 2 starts with a charge of -1 coulomb. That's a lot of charge, right? 3 coulombs is a lot of charge. Usually you see a question like this, might be nanocoulombs or microcoulombs, but it doesn't really matter. Process works the same. We've got a third one that has a charge of -5 coulombs. One of them touches another one, and then it touches another one, and we want to see what happens to them. Well, we know that charge will be transferred when I touch a couple of these objects together. We know that, when you touch that, you walk across the room with your leather-soled shoes on carpet and you touch the light switch, you get shocked. You know that if you walk across the room and you reach out and you touch somebody's finger, you and the other person get shocked. You know that charge will transfer from one object to another when there's a difference in charges between the objects to begin with. We're going to move charge back and forth there. But what's it going to end up being? What are the values going to end up being? Pay really close attention here. Charge number 1 touches charge number 2. The goal here is for those charges to balance. Electrons are going to move back and forth, but the net flow of electrons will be such that the charges will balance out. So how do we figure out what they're going to balance out to be? Well, if we look at charge 1 and 2, there's a total charge between the two of them of +2. Right? 3 and -1 is a total of +2. They're going to balance out to be +1. We add them up, we divide by 2. Now, charge number 3 is going to remain at -5 because it hasn't been touched yet. We added the first 2 up, we divide it by 2, became +1 and +1. Now it says the first ball then touches the third ball. What do they become? +1 and -5. What's the total charge among those? +1 and -5? -4. What are they going to balance out to be? Good. -2 and -2. And what's happened to the next? This one right here, the middle one? Nothing. Because it wasn't touched in this time, right? So these two guys touch each other, become +1 and +1. These two guys touch each other, become -2 and -2. Let's just do a final little check to make sure that everything is good according to the law of conservation of charge, that the total charge will remain the same. Let's add up the first line, see what the total charge of all 3 objects was before I started here. +3 -1 -5 gives me, what's that going to be, -6, -3? +1 +1 -5 gives me -3. -2 +1 -2 gives me -3. So all through this, the total charge remained the same. Charge wasn't created or destroyed. It was just moved around from one place to another. All right, 2 multiple choice questions. I'd like you to look right now at multiple choice number 32. This is in your booklet that you already have as well. At the end of your Unit 2 worksheets. And I'll ask you to submit this one, please, as multiple choice number 1. Okay, let's take a look at the 2 answers that we got here from people, A and B. It says 2 conducting spheres have identical surface areas. The reason that they say that, we don't have to worry too much about that in the questions that we see, identical surface areas, but they're just kind of prefacing the question essentially with some information in case you know a little bit more than the average person. Okay, they don't want you to be fooled if you know more. Okay, if you're smarter than average. Basically, charges want to balance out, but they can't balance out in all circumstances. If you have 2 objects that are dramatically different size or dramatically different shapes, then they won't necessarily balance out. For instance, if you've got one really, really, really massive aluminum ball and then one really, really, really tiny aluminum ball, and you touch them together, the charges won't completely balance out because the big one can physically hold more than the little one. They won't balance out. The goal is to balance out. They just can't. Similarly, if something is pointy and the other thing is rounded, okay, then the thing that's pointy will hold less charge than the thing that's rounded. Charge likes to leave things that are pointy. So they're kind of prefacing this question by saying they're equal surface areas. Basically, they're telling you, look, don't worry, they're going to balance out. you don't really ever have to worry, okay, because they'll all try to balance out. Okay, any question you get like this, they will balance out. It's just that they won't necessarily in every circumstance in the real world. That's all. So they have identical surface areas. A has a charge of 4.5 coulombs. B has a charge of minus 2.4. A and B are brought into momentary contact, then separated to a distance of 2.5 centimeters. First of all, this centimeters, we're going to circle centimeters because it's non-standard. But we know that we're not going to use that here, right? We're also going to circle this, although my answer's in microcoulombs as well, so I'm probably not going to have to worry too much about that. They touch each other, they balance out. What are they going to balance out to be? Well, 4.5 microcoulombs plus minus 2.4 microcoulombs is 2.1 microcoulombs. So B would be our answer, right? Daniel, why not? Good. You got to average them, right? That's the total charge among the two of them. Okay? Each one of them can't have that much charge. The total has to be 2.1 microcoulombs. So what we're going to do is divide that by 2. Add them up, divide by 2. Average them, right? And that gives me positive 1.05 microcoulombs, which means the answer is A, which is good because about 90% of you said A. Right? Hard question? Good. One more question we'll leave you with here today. A little bit of a different question. Just want to see what you can do with this before we wrap it up for the day. The number of excess electrons on a ball that has a charge of minus 3.6 times 10 to the minus 17 is what? All right, the number of excess electrons on a ball that has a charge of minus 3.6 times 10 to the minus 17. How are we going to go about doing this question? What if I asked you this question? What if I said you went to the grocery store, picked up a bag of oranges. One orange had a mass of 200 grams. The bag of oranges that you have has a mass of 600 grams. How many oranges in the bag? Without looking in the bag, how many oranges in the bag? 3. How'd you figure that out? Just divide it. Okay, 600 by 200 gives me 3 oranges, right? So we took the total mass and we divided it by the mass of one orange, and that told us how many oranges we have in the bag. Well, if we want to find out how many electrons we have, let's not take the total mass and divide it by the mass of 1. Let's take the total charge and divide it by the charge of 1. The total charge is 3.6 times 10 to the minus 17 coulombs. The charge of 1 electron is negative 1.60 times 10 to the minus 19 coulombs. I think when we do the division there, I think it works out to be 2.25 times 10 to the 2. Which would express A, B, C, D, A, B, C, D. The answer would be 2252. Now, I'm curious. There's lots of people that submitted answers for this, lots of different answers, but all of them looking like people did it the same way. The answers I got basically were, I think 3.58 times 10 to the 17. Where did that one come from? I'm just curious. 3.58 times 10 to the 17. Looks like lots of people had that. Lots of people expressed it differently, but looks like that's what lots of people had. Tom? Oh, okay. Does this make sense why you divide? Okay. When you think about that orange example, right? Like everybody understands how you're going to figure out how many oranges in the bag, right? We're dividing. So that's what we're going to do here as well. Listen very carefully to this. Whenever you want to find a number of anything in physics, divide. Divide the total something by the something for 1. So total mass by the mass for 1. The total charge divided by the charge for 1. The total momentum divided by the momentum for 1. The total energy divided by the energy for 1. You want to find a number of something, it's total over the amount for 1. Okay, that's it for today, guys.